Hello folks, and welcome to lecture number 3 in network security. You should be seeing some slides on your screen momentarily. Okay, so here we go. Last time we saw the TLS Handshake protocol, and just to remind you, here is a recap of what this did. We have these 4 messages in the protocol. There's a client hello, server finished, and client finished. And what happens briefly is that in the client hello, you send this diffie-Hellman message, G raised to a random power chosen by the client. There is the client knowns, NC, and a list of algorithms that the client is saying to the server, these are the things I know how to run. Which ones do you want to run? And the server replies with server hello, its diffie-Hellman message, its knowns, and the algorithm it chooses among those that the client was offering. You had then the server finished message where the server confirms that this is really me, and so on. So there's a certificate of the server. There is the signature from the server on all previous messages, and there is a MAC on all previous messages as well, using this server MAC key, which is something you generate from the diffie-Hellman shared secret, which you can compute at this point, and also the knowns and so on. The client will reply if it's happy about certificate and signatures and MAC. It will reply with its own certificate, its signature, and its MAC computed also on all previous messages. And if both client and server are happy about this stuff that they receive, then they will generate some application keys from, as it says here, the client, the diffie-Hellman shared secret, the hello messages and the server finish message, and then these will be passed to the record protocol and will be used for secure communication after this point. So what we then need to do is to argue about the security of this protocol. So we will not be able to do a mathematically rigorous proof for no other reason than because the definition we gave is also not mathematically rigorous. But we can argue on some intuitive level and get a feeling for why the protocol should be secure. So here's the protocol again. And for the authentication, you might remember from the definition that the definition is phrased in terms of which security guarantees can I, as participant in the protocol, expect to get, assuming that I accept the protocol and outputs a key. So here we see things from the client point of view. Let's say the client wants to talk to the server S and actually accepts in the end. Then we want to prove that actually the server did participate in the protocol. And as we know, because we get a signature from the server here, that where it signs all the previous messages, and this includes notably the knowns that the client has chosen. It's up here. So the client uses this in such a way that you're guaranteed that this has never been used before. So this means that you're guaranteed this signature that I get now from S is really for me for this instance of the protocol. It could not have been an old signature that some adversary is trying to send to me once again here. So as it was really out there. And then also if S on its side accepts, it must be because he wanted to talk to C. Because if that was not the case, then he would have rejected once he sees the certificate of C, because remember, certificates contain identities and public keys. So if S would see the wrong identity in the certificate, then of course he would reject and say, that's not who I want to talk to. Okay, then we have a symmetric argument. If we see things from the server point of view, we can basically run essentially the same argument to show that then the client must have been out there, and if the client accepts it because he really wanted to talk to me. Next property is secrecy. So again, seeing things from the client point of view, if he wants to talk to us, if he accepts, then we want to show that the server S must be the only other party who can compute the application keys that the client outputs. And the reason for this is, well, first of all, again, the server has signed all previous messages here. So this means in particular that it has signed this particular server-side Diffie-Hellman message. And it must be the same one that he sent and that we receive here, because, I mean, we know what we received, and it was the same thing that the server signed. So G to the RS actually comes from S. And furthermore, we also get this MAC on all previous. So the thing is, S could generate the correct MAC. So he must know the MAC key and hence also S. And therefore, S is the only other party who can compute the application keys, because you can't compute the key unless you know S. You can run a symmetric argument again, saying, well, if S accepts, then C is the only other party who can compute the key. Then we have agreement. So we want to say, again, if C accepts at the end of the day, then you want to be sure that the key that the other guy outputs, if he accepts, actually is the same key that we output on the client side. And so again, S has signed all previous messages. So this means that we agree with, that the client can conclude that the server must agree with me on the hello messages, because that's exactly what was signed here. Also, the adversary cannot, because then the question is, do we also agree on the server finish message, right? Because you might remember that the application keys are generated from the client hello, server hello, and server finish messages. So if the client can be sure that you know, I must agree with the server on those three messages, then we also agree on the key, on the keys, on the application keys. Well, so we certainly agree on the hello messages, and also then if you look at the server finish thing here, well, an adversary could of course try to manipulate this stuff here. But the thing is that you cannot really change the certificate of S here for a different certificate for a different party, because C wants to talk to S, right? So you can't really, you know, put in a different certificate with a different name than C would reject. And then, of course, if you cannot change the certificate to something else, then you cannot falsify the signature here. You have to simply relate the signature and the MAC that the server has set. So this means that we agree on the first three messages, and therefore we also agree on the keys. The freshness is really simple. It simply holds because nonces are fresh, and they go into what is used for generating the keys. So as long as C knows that I choose my nonce, so it's fresh, then you also know the keys are fresh. Okay, so that's sort of on a somewhat loose intuitive level why the TLS handshake is secure. There are some variants of the handshake. One variant is this one-sided so-called handshake, which is something that pertains to an important use case for TLS, namely that you often want to execute it in a case where you cannot really do it according to the original description, because C the client does not have a certificate and a secret signature key. So what you do in that case is you simply do the same protocol, but you drop from the protocol everything that requires a certificate. And what this means concretely is that a client finish message would only contain this MAC that's done on all previous messages. You simply drop the client certificate and the client signature. This works, except of course that it means that the client knows he's talking to S because he gets certificate and signature from the server, but of course S has no idea who C is. Whoever managed to come up with a MAC on all previous messages here must be the guy who is able to generate the same Diffie-Hellman key that I can generate, but who that is, you have no idea. Now, if you still want to authenticate the guy out there, you can still do that, for instance, using a password. So if C has a password that S is able to check, then once you have established the secure channel, then on that channel, you could then send the password. This works because from the client point of view, so she knows she's talking to the right server, and so it's okay to send your password for that server on the channel because the tunnel actually ends in the right place. It will be the right server that receives the password. And on its side, the server now knows what's out there once it checks the password. Okay, so then we have one extra thing. So actually, the handshake you've seen is simplified a little bit. So what happens in the real version actually is that when the MAC keys are generated, we also generate some temporary encryption keys. And what these are used for is to encrypt the rest of the handshake. So that means the two finished messages. This is not a problem for security. It's quite clear that this can only make it harder to break the protocol. It only makes it harder for the adversary to manipulate those messages when they are encrypted. But the advantage, on the other hand, is that it means if you were sitting on some network hub and monitoring some channels that trying to see who is trying to connect, then you will not be able to tell, because when this finished messages in the protocol are encrypted, that means that the identification numbers, the names and certificates are also encrypted. And that's the only thing that can tell you who is trying to connect to you. So if you were an eavesdropper trying to target a particular person, this would make it harder. So that then finally gives you the entire picture of the TLS handshake. Okay, so there are also other ways to do similar things than what TLS does. In particular, there is something called IPSec. And to make a long story very short, is IPSec does exactly the same thing as TLS, but instead the parties who are talking to each other is not going to be a client and a server, but it's going to be two IP nodes, so two entities with an IP number. So that would typically be, for instance, the network adapter in your laptop. So IPSec is placed in a standard protocol stack inside the transport layer. So this means that what goes on here is basically encryption between two IP nodes, and it means that the content of the TCP IP packages that you send will be encrypted. So the parties who talk, again, that's the main difference. These are typically hardware components with IP numbers, and not pieces of software such as web servers and web browsers, as it would be for TLS. IPSec has a handshake based on the Diffie-Hellman, typically just the same thing as TLS. So should you use IPSec or should you use TLS? And the answer is it depends. They're actually incomparable. Because on one hand, if you use IPSec, the good thing is that your network adapter typically has the encryption, and that means that whenever an application is running on your machine, it can actually take advantage of the secure connection without knowing anything about security. Whatever is put into the tunnel goes through in encrypted form and makes it to the other end, hopefully unharmed. Whereas on the other hand, for TLS, you really have to be a TLS compliant application to use TLS, of course. So that is why IPSec is often used for implementing something like virtual private networks. So where you logically, even if you're physically in a different place, you can logically be placed inside some private network somewhere. And this is done using IPSec because it means that everything running on your machine will be using the encrypted connection. On the other hand, though, with IPSec, the secure tunnel ends in the network adapter. So when it spits out data from there, it's in plain text. Whereas with TLS, the tunnel extends all the way to the application that's running TLS. So this means that TLS can be used to separate applications in a multi-user system. So what this means is that if you have a multi-user system that runs on some machine, then so we have maybe different users using different instances of a web browser, then you can use TLS to make sure that one browser cannot read stuff that's meant for the other browser. Whereas this would not be the case. The separation would not be the case if you're using IPSec. So, there can be different reasons for using those different systems. Okay, a final concept I want to talk to you about is something called Password-Authenticated Key Exchange. So this is about this question. We talked about this before, actually. What to do if a user wants a secure connection to a server, but the user only has a password. It has no certificate. We saw before that you can use one-sided TLS plus the password. But one could ask, why do we jump to all these hoops with certificates and public key stuff and everything if security anyway is only as good as the password security? And it's a fair point. People have tried to answer this by designing something called Password-Authenticated Key Exchange, where we simply say, okay, if the password is all we have, then let's base the authentication in the key exchange on the password directly. Which actually sometimes means that you can more easily implement stuff. So there are some issues with this though, because as you know from the key management section of the course, passwords usually cannot be taken from a very large domain, because it must be possible for a human to remember a password. So you can't really have very, very long passwords, at least not if they're supposed to be randomly chosen. So usually the number of different possible passwords is not really that large. And this is a problem because if the adversary gets enough information that he can brute force the password offline, then you're dead. So what this means more concretely, for instance, is suppose the adversary gets a hash value of a password of some user. So the hash password. This is in fact something that you would often find, say, in a password file on a Unix system. So if the adversary gets such a hash value, then what he can do on his own machine, as fast as he possibly can, is to run through all possible passwords, hash every candidate, and compare with the hash he was given, and then figure out what the right password is. So that's what is meant by brute forcing a password offline. And of course, this would be a huge advantage to the adversary if he can get to do this, because the only other attack that would be around is, so if the adversary cannot brute force the password himself, then all he can do is he can try and guess the password and test whether his guess is correct by simply trying to log into the system. And this is a very slow way of checking your guess, because the target system that you are attacking, can notice that why is this guy logging in all the time? Something is wrong, and we can slow this down. This is what many systems do. That once you enter an incorrect password, then it takes more time before you can enter the next guess. If that's also incorrect, even more time, and so on. And that's something that the system does in order to slow down an adversary. So that's something that can make it really, really hard to guess the password if that's the only attack that there is. On the other hand, it's also an attack that we cannot possibly prevent. You can always try and log in with a guessed password. So if we can make a password-authenticated key exchange where the only attack the adversary can do is this stupid attack here that we cannot prevent anyway, then that's the best we can hope for. Okay, so let's see how to do this. So here's a simplified example of the main idea. So now we have, again, the client and the server, but now all they have is a password in common. I'm assuming here that the server knows the password in the clear, which shouldn't really be the case. But for simplicity, we assume this. There are also examples of password-based AKEs where the server does not have to know the password in the clear. Okay, so but the idea is the following. So the client will make a Diffie-Hellman message, the usual thing, G raised to the RC mod B, and then encrypt that thing, this number, under the password. So this usually means something like you take the password, run it through a hash function, and use the output as an encryption key. Using this over, the server does exactly the similar thing, encrypts also under the password his thing, and now both parties can decrypt onto the password this Diffie-Hellman message, and from the Diffie-Hellman message you get the shared key. And then you do some steps where the parties confirm that we really agree in the previous messages. This can be done using Macs and stuff. This is standard stuff. But the main thing is this first step where you do Diffie-Hellman, but on the encryption of the password. So why would this help? Well, the point is that if the adversary would try to impersonate the client, then the problem, of course, is that you don't know the password, so you cannot encrypt this thing under the correct thing. And therefore, the server would get, a garbage value when decrypting under the correct password. So there's no way you can successfully get a successful development key exchange with this guy. And also, what about this thing here? If the adversary gets the eavesdrops the communication, would he be able to brute force the password based on this? And the point is that the answer is no, fortunately, because we assume that this encryption scheme has an important property. If it is the case that you take this encrypted message here and you try and decrypting it with some other password prime, let's say, then the assumption is you just get some number modulo p. In other words, you don't get something which is obviously wrong. And this is a big advantage because this means that if you're trying to brute force the password offline using this communication that you eavesdropped, then you will fail, because every time you guess a password prime, for instance, and you try decrypting, you'll get a couple of numbers. They look just like any other number modulo p, and you have no reason to believe that those were correct or incorrect. So there's no way to verify that your guess was correct, and therefore you're back with the old attack, where the only thing you can do is to actually try and simply log in with whatever password you guessed. Okay, so that's what I wanted to say about password-based authenticated key exchange. There are protocols out there that are standardized and are implemented out there. So password-authenticated key exchange is a possibility also in real life. Some final words about the limitations of this stuff we've seen. So all this TLS IPSec stuff is great, of course, but there is a limitation, which is that it only provides secure tunnels. So once data leaves the secure tunnel, it's no longer protected. And so what that means is that if what you really wanted was encryption or signatures that pertains to a particular document, so you want something you can store such that it's in encrypted form and signed form, then TLS and IPSec cannot really help you with that. But there are other stuff out there. Other formats, other protocols can do this. For instance, if we have secure MIME for secure email, and also XML, PDF are documents format that have room for signatures and encryption inside the format. So there are ways to do this. There's also software out there that can help you do this kind of stuff. So I think this was basically it. This was the end of the final lecture on network security. Thank you for listening.